development using SAS. And we have been discussing statistics over the last couple of sessions, right? So which we continue till today, which we continue today as well, right? So basically, what we tried doing was we were actually covering the different concepts of basic statistics, and in the last class we had discussed about the basic concepts of central tendency and dispersion, right? And within that, within the basic concepts, what we have discussed about was what exactly is mean, what are the different type of mean, what are the different challenges that mean, median, and mode has. So which one has an advantage over the others, which one is a better option, so which one is good, which one is bad, and what are the respective challenges of them. So having said that, the next part that we talk about today is we'll be talking about some of the measures of asymmetry, and we'll be talking about what a symmetric distribution is, what an asymmetric distribution is. Also, before that, we have had a brief discussion on these concepts, right? So basically, in today's topic, we would be talking mostly about the basics of skewness and the basics of asymmetry, and from there we'll move on to talk about the other different kinds of. So we'll just move on to talk about the other different kinds of techniques and stuff. So, having talked about the major measures of central tendency and about the measures of dispersion, right? We saw that broadly there are so we have the absolute measures of central tendency, the absolute measures of dispersion, as well as relative measures of central tendency and the relative measures of dispersion, right? Now, what is it that we do, or what is it that we try to understand, or what is it that we can interpret about the behavior of a variable using these factors, or using the measures of central tendency, dispersion, etc. So, the question that we try to answer today is how do we use these measures to create insights? So, how do we create insights using these measures? Create insights using these measures of central tendency and dispersion. Excuse me. How do we create insights? Now, most of the cases, what we need to do is, or most of the areas where these descriptive measures are used, is to understand the shape of a distribution. So broadly, they are used to understand or to assess the shape of a distribution. Assess the shape of a distribution. Assess a distribution. So when I talk about a distribution, so basically when I'm talking about about using these to assess the shape or assess the properties of a distribution, the first and the foremost concept that we need to discuss over here, that we need to explain over here, is what exactly is distribution, right? How do we define a distribution? And once this distribution is defined, the next part that comes to us is we try to understand the descriptive. So basically we try to understand how we use mean and variance to assess a distribution. So what is a distribution? So when I talk about a distribution, what I simply mean is a relative frequency distribution. So a distribution is a set of the values of a variable and its relative frequencies plotted together. So it's a relative frequency distribution that I am essentially talking about. Frequency distribution, right? So when I talk about this relative frequency distribution, so let's see how this distribution looks like, or what exactly is it all about. So basically I have this variable, say x, and this variable x has certain relative frequencies. So over here, say I have this variable x, and for each outcome what I also have is a frequency, and from them what I get is a relative frequency. So it is fi by n. Now the outcomes over here are x as the value x1, x takes the value x2. Like this, what I have is x takes the value xn. Now the frequency distribution of x1 is f1, x2 is f2, xn is fn. So f1 shows the number of time x1 repeats in the data set. Right. So if f1 is equal to 1, it means that this variable x takes the value x1 only once. x2 takes the value twice, x3 takes the value thrice, xn takes the value fn times. So similarly, so therefore from this frequency, if I add up all the frequency values, what I get is the sum total of the observations. So what I get is capital N. So capital N is nothing but the sum total of the observations. Now after that, what I will come up to is the relative frequency distribution. So it is f1 by n, f2 by n, and what we'll have is fn by n. So this is the relative frequency of the various outcomes. So relative frequency shows the chances of xi to occur relative to the overall occurrences, right? Now when this is done, the next part that we do over here is, the next thing that we need to do is we need to plot this graph, right? So basically on one axis of the graph we have fi by n. On the y-axis we plot the relative frequency, and over here I plot the independent variable x, right? So over here, so this graph over here, you have fi by n, and over here what I have is xi. So over here what we'll see is the values of xi on this axis and the value of the relative frequencies on the y-axis. What we do is we plot the distribution. So when I plot this distribution, say I can get a figure like this, right? I can get a distribution like this, or I can get a figure like this, or I can get a figure like this, right? So for this blue line and for this amber line, what you can see is that for both of these two lines, the concentrations happen at one end. So for the blue line, the concentration happens at the lower end values. And for this amber line, the concentration happens at the upper end values. So when this happens from here, what I can clearly say is that yes, this is the distribution. So over here I can see that for both the blue and the amber line, the concentration happen at one end. So for the blue line, it happens at the lower end values. For the amber one, it happens at the upper end values. And there is a sparse, there's a sparse spread of the values at the tails. So this kind of a distribution is called an asymmetric distribution or a skewed distribution. So this kind of a data set or this kind of a distribution represents a variable which contains different heterogeneous groups of values. So over here in this case, what you can see is that this distribution that I have is the skewed data. So this is the right skewed data. This is called a right skewed data, and this is called the left skewed data. It's called the right skewed data because the skewness happens towards the right hand side. So majority or the concentration of the variable values over here happen towards this left side, and the skewness or the asymmetry or the tail end values or the spread happens over this side. That means the skewness or the asymmetry arises due to extreme values or very large values which lie towards the right end of the line. Hence, this distribution is a right skewed distribution, or it is also known as the positively skewed distribution. On the other hand, if I look into this particular distribution marked by the amber line, you will see that the concentration of the values or the representative values lie towards the right hand side, and that there are a few heterogeneous values towards the tail end at the left hand side. Therefore, this skew is called the left skewed distribution or the negatively skewed distribution. So the right skewed distribution is also known as the positively skewed distribution, right? And the left skewed distribution is called the negative skewed distribution. Whereas on the other hand, the green line, the distribution of the green line is a very symmetric distribution. So it shows that the concentration of the values do not occur at one given end of the series, right? It happens in the mid, it happens near the middlemost values. Hence the distribution is very symmetric in nature. So if a distribution is symmetric in nature, it visibly implies that there are no undue concentration at the ends of the axes, right? Hence this is called a symmetric distribution. A symmetric distribution forecloses the occurrence of outliers or extreme values. Basically, if I have a symmetric distribution, what it simply means is it forecloses the occurrence of distribution. forecloses the occurrence of extreme values or outliers. Extreme values or outliers. Right. So there is a right skewed distribution and there is this left skewed distribution as well. So the next question. So basically, the objective of using mean and standard deviation, mean and variance, or mean, median, mode, and variance, is used to assess the shape of a distribution. So by looking into the mean, median, and mode values, we should be able to identify the whether a distribution is a skewed distribution, a symmetric distribution, or if it's a skewed distribution, what kind of a skewness does this distribution have, right? So is this concept of skewness clear to us? Great. Now what will happen is we'll take up each of the distributions one at a time. So we'll take up a right skewed distribution, we'll take up a left skewed distribution, and we'll take up a symmetric distribution one by one. And once we have those values, once we have gone through them, the next thing is we'll start talking about that how we use mean, median, and mode to infer about the shape of the distribution. Yeah, Srinivas, you had a question. Please ask. Okay, so the concept of expected value I'll explain to you when we go into the probability section. So I have to explain expected value over there. So till now, just keep in mind that expected values is nothing but it implies average values. Okay, okay, Srinivas, not a problem. Okay, so we'll take up each of the distributions one at a time and then we'll try and explain. So when I take up a right skewed distribution, we'll talk about the cases where we get to see right skewed distribution in risk, in the domain of credit risk, and then we'll talk about that. So let's start off. So over here, what I'll have is I'll have the value of the variable x. So this is on this axis, I have the values of the variates. Variate values, right? On the second side, what we have is the relative frequency. So we have relative frequency. So just let me plot this distribution over here. So this is what the distribution is. So over here what I have is, so this is your distribution. Now, and obviously I can understand that this is a right skewed distribution. So over here, if I need to understand that how do I identify a right skewed or a left skewed distribution using mean, median and mode. Now, if we look into the shape of this distribution, we'll see that over here towards the lower end values, there is a huge concentration. So there is a large concentration of the values at the lower end, right? So towards the lower end values, and there are a few sparse upper end or tail end values over here. That means this case is very similar to the case where there are one or two extreme high end influential observations or high end extreme values, right? So therefore, the average value will be biased towards the upper end values. So if if you have a tail end values over here, the average will be more representative or will be more closer to the higher end values than to the lower end values, right? So over here, if I have a look into this, so this part undoubtedly is the mode of the distribution. Now, why is this the mode of the distribution? Because corresponding to this value, the frequency is the highest. So this is the mode of the distribution. So this is nothing but the mode of the distribution. Okay. Now in the next part, if I have a look into this, now where is the median? Now you see that this distribution is defined over over this entire real line, right? So obviously the midpoint of this line or the median will be that value which divides this entire line segment into two equal parts. So this part is most likely the mode of the distribution. So what I have over here is the mode, but the median of the distribution. So it is this line which divides the distribution into two equal halves. So this is the median of the distribution. Now where is the mean? Obviously the mean is a value which will be which will be farther away from the median. I mean from the from the most representative values. So basically the mean will be more closer to the tail end value. So and hence the mean will be placed somewhere over here. So this is the part which is the mean of the distribution. Right? So this is the mean. So if I compare the mean, median and the mode, I should be able to identify the shape of the distribution. So basically for a positively skewed distribution, the mean is greater than the median, and the median is greater than the mode. So mean is greater than the median. Greater than the median. Right? So this is what happens for a positively skewed distribution. For a positively skewed distribution. Yes, Srinivas, I'll share the class notes. Right? So this is how we can identify a skewed distribution from by using mean, median, and the mode. So for if a distribution is a skewed or an asymmetric distribution, then the mean, median, and mode will be of different values. Clear? Great. So now after this, the next part that comes out here is the left skewed distribution. So now let us look into how would it be for a left skewed distribution. Okay. So now for a left skewed distribution, the distribution would look something like this. So I'll have the variable values x, and I'll have the relative frequency distribution over here is Fi by n. Right. So say I extend this value like this. Let's have a look into this distribution. Now obviously for this distribution I can see that the mode lies towards this value. The mode lies, so this is the mode. So this is the mode of the distribution that I have, because this is the value which occurs with the highest frequency distribution. Now the median is again the midpoint of this line segment, so which is towards this one. So which is the median over here. So the median is the line which divides, or median is that value which divides this line segment OX into two equal halves. Now this distribution contains some lower end extreme values. So the existence of the lower end extreme values will pull down the mean and make it more representative towards that. So that is why the mean will be near to here, right? So it is the existence of these very you know, it is the existence of these low end values which makes this distribution uh, left skewed. So and the mean will be pulled down, right? Now in this case over here we can clearly see that the mode is greater than the median, and the median is greater than the mode. So the median is greater than the mean. Right? So mode is greater than the median and the median is greater than the mean. Now this happens for a left skewed distribution or a negatively skewed distribution. Left skewed. So the left skewed distribution is representative of I mean represents it represents a data series or a variable value set of variable values where majority of the values are towards the higher and upper end values, and there are some relatively lower end extreme values as well, right, which creates all the problems over here. So going by that I can clearly see that yes, this relative distribution value is so this distribution is less skewed because there are a couple of these lower end values which is creating the entire problem, right? So for a negative distribution, so for a negative distribution, for a negatively skewed distribution, we'll get to see that the mode is greater than the median, greater than the mean, right? So at the crux, if the distribution is skewed, I can see that the mean, median, and mode are very different from each other. Okay, so Prakash is a question over here. Can we draw the distribution for a mix of positive and negative values? Yes, we can draw the distribution for a mix of positive and negative values. So if you have mainly if you have negative values at one end, then those are lower end values, and if you have some positive values, they're from the tail values, or it can be symmetric, or it can be right skewed as right skewed or left skewed. So obviously you can do draw for a mix of positive and negative values. However, for risk, most of the variables take a positive value apart from growth rate or percentage changes. Most of the primary variables and their values take the absolute positive figures, right? Great. Okay. Now, so basically, what you can see is that whenever a skewness arises, the data set, the variable contains two or more heterogeneous groups of values. So over here in this case, what you can see is that this part represents a group of values, right? And this part represents another group of values. So it is the existence of coexistence of these two heterogeneous groups of values. These are very high end values and these are very low end values. So the heterogeneity of these two groups of observation punched together creates the skewness, right? So if a variable contains, or if the set of even if a variable contains a very homogeneous group of observations, then that distribution is considered to be very symmetric in nature, right? So how does a symmetric distribution look like? So a symmetric distribution looks like, so as the word symmetric implies that if you actually split the distribution into two equal halves, then what you get to see is that the distribution will be very, I mean, the two halves of the distribution will be will be a mirror image of each other. So basically, if this is the variable x that I have, and over here what I have is fi by n, the relative frequency distribution. So this distribution is more or less symmetric in nature, right? So the idea over here is if you actually split this data or this distribution from in between, right? So this side of the distribution and this side of the distribution will be absolutely symmetric in nature. They will be mirror image of each other, right? So this is called a symmetric distribution, and for a symmetric distribution, the mean equals to the median equal to the mode. So mean equals median, which is equal to the mode, right? And this is therefore called a symmetric distribution. So in a symmetric distribution, you only have a homogeneous group of values and you do not have two or more heterogeneous category punched into it. So this is why this variable values, or this variable is called, or the distribution of the variable is called a symmetric distribution. So the existence of symmetric distribution forecloses the existence of any outliers. So over here you can clearly see that there are some extreme values or outliers, but over here in this case it is not so. So these tails are evenly spread. So the tail end values are evenly distributed. So the tails are even in nature. So for a symmetric distribution, the tails of the distribution is very symmetric in nature. Tails of the distribution is symmetric in nature. Is symmetric in nature. Right. So over here, so these are the three broad types, or three types of distributional shapes that we get. However, one more thing that you can observe over here is that each of the distributions that we have created over here has one single mode, right? So there is only one point where the distribution peaks. Therefore, these distributions, all these three distributions that we have plotted, are said to be unimodal in nature. So that is the distribution or the relative frequency distribution such that it peaks at only one point, or there is a one unique mode. That is, the distribution is unimodal in nature. Right now, however, you can also have bimodal distributions as well. You can also have bimodal distributions, and bimodal distributions look like this. Right, so a bimodal distribution would look something bimodal or multimodal distributions. So over here you have multiple points where the distribution is picking up. So this is one point, this is another point, this is another point. So this distribution therefore is called the multimodal distribution. The multimodal distribution. Right. So is it clear up to this point? Great. Great. So, having said that, the next part that we talk about over here is we just introduce the basic concept of skewness, right? So basic formula or a basic function which can be used to understand, which can be used to understand skewness. So one very specific formula, one very simple formula for skewness is that of is Carl Pearson's formula, or Carl Pearson's skewness coefficient. Carl Pearson's formula for skewness or skewness coefficient. So what I'll denote is I'll denote skewness as SK. So it is mean minus mode so mean minus mode by standard deviation. So this is Carl Pearson's formula for skewness. So basically, if I see that mean minus mode by standard deviation is greater than 0, that is mean is greater than the mode, then you know that obviously yes, the distribution is right skewed distribution. If it is less than that, you know that it is a left skewed distribution. Right, so this is a very basic formula to capture the Carl Pearson's formula for skewness. Right. Okay, great. So having said that, so these are the three basic measures, these are three basic descriptive measures. One is measures of central tendency, the other is measures of dispersion, the third is measures of asymmetry. Now, having said this, now we have framed our idea about on what grounds can I actually assess the behavior of a variable. And by looking into these, we can actually make out that what type of a variable are we dealing with actually. Now, let us look into some examples of such. We have been talking about distributions and stuff. So what exactly, or where do we find these examples, or what type of an example that do we find in risk which represents these distributions, or we can actually use them to assess the properties of these distributions. So one very important example is one very common example which comes to my mind is the loss distribution. Is the loss distribution of a bank. Loss distribution of a bank. So the question that comes out is, what do you think would be the shape of the loss distribution? This is what we tend to answer now. Right, so how would the loss distribution actually look like? How would the loss distribution actually look like? So if I want to understand how the loss distribution would actually look like, let us try and understand the loss structure of a bank. Right. Start off with loss distribution. So the loss that a bank actually earns is comprised of two parts. One is called an expected loss. So one is called an expected loss. One is called the expected loss, and the other is called the unexpected loss. Now let's try to understand each of these concepts. Now, if I say that it's expected loss, what does it mean? That these losses are, they are, very frequently occurring losses. These losses, they occur very frequently. So that is where this unexpected loss or this question of unexpected loss actually comes in. The question of expected loss actually comes in. Now, the characteristics of expected loss is that these are losses whose frequency is very high. So, but the exposure is very small. So, expected loss, what happens is, so in an expected loss, frequency is very high. Frequency is high, but the exposure is small. But the exposure is small. So basically, the amounts of losses that we earn is actually very small. So it can be as small as 0.8% or 0.2% of the total exposure and so on. So this is the characteristic of an expected loss, right? And when we talk about credit risk modeling, we try to mostly manage this part of the loss modeling. So mostly we try to develop models for managing the expected loss. Models of, yes. So losses which I expect to happen and which I am trying to predict. And for predicting this expected loss, right? We have all these models of probability of default. I have models of loss given default. I have probabilities of exposure at default, etc. Right. So this is what expected loss is. And the biggest characteristic of expected loss is that these are portfolio losses, right? So losses arising from obligor lending and obligor borrowing, etc. And therefore, their exposure relative to the overall exposure is actually very small. Now, unexpected losses. Now, unexpected losses have a very rare frequency of occurring. And when I say, I really mean very, very rare. So they have a rare frequency of occurrence. frequency of occurrence. And their exposure is very huge. And the exposure from these unexpected losses can be to such extent where our entire bank may collapse. So basically, say this arises because of a sudden wide crash in the stock market, so the entire financial system disrupts, or a war breaks out. So suddenly, what happens is the entire financial balance of the economy goes for a toss, and that is where there is a huge amount of exposure. So the exposure is large. This one such event where we saw such large exposures coming out is the case of 2008 financial crisis. Right, to model this unexpected loss is, so we use the entire Basel model framework to model this unexpected loss. Right, so we have all these regulatory models of CCAR, DFAST, etc., Basel and everything to model these unexpected losses. So therefore what I can see is that there are two types, two different kind of losses, or two different nature losses of two different natures being punched into one. Being punched into one. Therefore, from this case, I can make out that this distribution is going to be a right skewed distribution. This is the right skewed distribution. Therefore, the loss distribution of a organization, loss distribution of a bank is a negatively, it's a positively skewed distribution. Clear? So the loss distribution of the bank would appear something like this, or it would look something like this. So what I have over here is, I'll write it as the loss, or the percentage losses. And this is where I have the relative frequency. So obviously the graph of this distribution would look something like this. Right? So the expected loss that I have, so the expected loss that I have over here will be something like this. So this is your expected loss. the expected loss, right? And this expected loss is covered up by the provisions. This expected loss which is covered by the provisions. Right? Clear. So this is one example of a right skew distribution in the domain of risk. So the bank's loss distribution itself is an example of a right skew distribution. Okay. So now coming to the next question, I said that expected loss, I mean, this is covered up by the provisions. So what are provisions? Provisions are a part of the bank's net profit kept aside, I mean, a part of the bank's profit kept aside to meet the expected losses, to meet, the provisions for bad debts, the amount which can arise as a default. So it's a part of the bank's profit kept aside to meet the bank's debts. Part of the bank's profit, part of the bank's profit to meet defaults, to meet bad debts or NPAs, the bad debts. To meet the bad debts. Clear? So provisions is a part set aside from the bank's profits to meet the bad debts or the possible bad debts that can happen, right? So that is expected loss, and that expected loss is used to meet these allowances on loans and lease losses. So when we come to these technical terms, we'll cover a lot more about them. But over here, as of now, let us start and try and understand the very basic uh, concept. So this is what the example. So this is how we can say that the loss distribution of a bank is right skewed, because it is comprised of two kinds of losses into one single variable. One is expected loss, which are high frequency, low exposure, and unexpected loss, which are very rare events but have very high exposures. And once they happen, they just create. They can even result in the collapse of the entire bank or the banking system. Right. Okay. So this distribution. So to your question, Preeti. So Preeti has a question. The distribution is for EL. However, we are saying UL is right skewed. So how to show the UL distribution? Okay. So Preeti, it is not a EL distribution. The EL is this point. The expected loss is the mean loss that the bank can actually earn, right? So that's more or less the predicted loss or the expected loss. Now the unexpected loss is the deviation about the expected loss. So an unexpected loss is nothing but the tail end values of the losses. So it is the tail end value of the loss, right? And beyond this unexpected loss is a potential loss. So a potential loss in this distribution is that part after the unexpected loss where which does not generally occur but may occur, and the probability of this potential loss to actually occur is as low as to occur once in every 1,000 years, right? So over here the unexpected loss is nothing but the variation or the variance about the expected loss, right? So the unexpected loss is the tail end value which has a high exposure but a very low probability of occurring. And the expected loss is not the distribution, expected loss is the mean of the loss distribution. Okay. 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 So to your question, Prakash, so do we have a similar graph or terminology to plot the impact as well? Now, when I'm plotting the impact, right, when I talk about plotting the impact is not plotted like that. The impact is generally calculated through different capital calculation formulas, and through specific sensitivity analysis, right? So over here we just plot the variable and its relative frequencies, that is the relative chances of occurring. So it shows that the lower exposure losses are more likely to occur, and the high exposure losses are least likely to occur. So that is why it's the loss distribution takes this shape. Now to examine the impact of a particular loss, there are separate procedures. There are certain estimation procedures which will give you estimation as well as sensitivity procedures, which will help us assess that okay, if this is what the probability of default is, or if this is the loss which occurs, then what is the impact on the probability, and then how does the capital then how should the capital requirements be changing, and so on. So those portions are there, but they'll come down in the later part stages of the discussion. Great. So now I have a question for the participants. So my question is, we have been talking a lot about mean and variance and a lot of these. Now tell me, for a given data set X, so I have a set X which contains some observations. I compute the mean and I compute the variance. Is it possible that the variance of the data set or the standard deviation of the data set is higher than the mean? Can the standard deviation of the data set of a data set be higher than the mean of the data? If yes, why? If no, why not? So my question over here is that can the mean of our data set, I mean the standard deviation of our data set, so can the standard deviation of our data set be greater than its mean? If yes, why? If not, why not? So while you answer this, I'll just take a couple of minutes break and I'll be back. Okay. So all the three of you are, I mean, more or less close to what the answer is. So I'll just give you a case. Okay. So conventionally, standard deviation can never be great, should not be greater than mean. I mean, it's never is. So it can happen if, for a case, if there is a huge concentration, or there is a significant concentration around zero. Because if there are many observations of a data set as is equal to zero, then the average value goes down. But when you subtract the mean value from zero and square it up, that value actually increases, and hence the standard deviation tends to explode, whereas the mean goes down. Therefore, if in a dataset X there is a concentration towards zero, Then you have numbers like the 35, 28, 60, something like that, right? Now, these zeros will pull your average down. Pull the X bar down. And when you do that 0 minus X bar whole square into n, the number of times you have 0, then this component will pull the standard deviation up. So this part will cause the standard deviation to shoot up, right? Hence, your standard deviation will be greater than the mean. So this is a typical case of a left skewed distribution. So your standard deviation can be greater than the mean in case of left skewed distribution where a majority of the value is concentrated at 0, where there is a significant concentration at 0. Right? So for left skewed distribution, what we see is that yes, the values, I mean the standard deviation, can exceed the mean if there is a concentration at 0. Right? Now, over here, I'll just share out one example with you. Right? So one of my previous experiences. So basically, we had a variable. So I was working on one of the provisioning models, one of the regulatory models, right? So I was working on FAS 5, so for financial accounting standards models. So when I was working on this FAS 5 model, so basically what happened was, so we had this case over there. So I had a case of amount outstanding, amount outstanding, right? And all the accounts which were there with me. So I had this data. I had this. I had the reading on this variable for all accounts which were on the books of the bank. There were accounts which were there on the books of the bank. Accounts on the books of the bank. Right. And what we saw was for this amount, for this variable, the standard deviation was greater than x bar. Right. Now, now when we looked into the variable values, so when I looked into the variable values, I saw that there was a lot of zeros involved in it. Right. Now, can you tell me what was the problem with the variable? So I had the variable value like amount outstanding for all the accounts which were on the books of the bank. So which were presently active on the books of the bank. and for that variable the standard deviation was greater than the mean. And what I saw was that all there were a large number of observations which had zero readings, which had zero values, and that is why the standard deviation has shot up and the mean was there. So what do you think was the problem with this variable? Was it okay to have that, or was there some basic problem, or there was some problem that could have been worked around? uh, Srinivas, I did not get your point. Could you please explain? Right, right. So yes, Srinivas, you are absolutely correct. So if an account is already on the books of the bank, then the amount outstanding cannot be zero. Right. So that is where the basic flaw of the variable was. So basically what happened was, when it was investigated and followed up, it was seen that the person who had entered the data, right, so it was a manual data entry method, so that person had substituted those zeros for the missing observations. So basically, if there were accounts, if the accounts were open on the books of the bank, that means they are presently pursuing, they are cutting on their installments, so they're cutting out their installments, and they are still in the process of repayment. Therefore, at any given month, their observation, I mean, the amount outstanding has to be greater than zero. It can never be equal to zero. And if it is equal to zero, that means there was some challenge. And when we followed it out, it was seen that those were actually missing observations, which was put down as zero. Right? So this is why, so this is how, by looking into the using these descriptive measures, and by looking into these variables, what we can actually make out is that, so basically what we can ideally make out is that what exactly, so basically we can actually make out important insights from the data, right? So that is something that is very important. We need to know how to use these descriptive measures and to frame out an insight from the data, so that if there is any abnormality, we can actually capture that by looking into the descriptive measures. And the descriptive measures are such that if there are any abnormalities, they will reflect the measures. All we need to do is to interpret them appropriately. Clear? Great. So from here, so this is the part. So with this, we come to the end of the descriptive measures, right? So we have discussed the measures of central tendency, the measures of dispersion. We have seen an example of a skewed distribution, the way it is in risk, and so on. We have looked into the different types of mean and which type of mean do we use for what variable, what are the respective limitations and advantages of the variable of the different means, what is median and mode, how do we use them to frame an insight about a distribution and so on, right? Now the next part that we need to talk about is, so till now we have been talking about a variable, right? Any variable x which has some observations. Now we need to introduce the concept of stochasticity. So next, our objective is to introduce the concept of stochasticity. Stochasticity, or as we know it as probability, right? So to assess the concept or understand the concept of stochasticity, we need to discuss the theory of probability, right? To assess probable stochasticity, we'll assess this in light of probability. Now the question that comes out is that why suddenly am I talking about stochasticity? Because till now I have just been talking about a variable, any generic variable with a certain outcome, and it has a measure of central tendency and dispersion. Right? However, dealing with risk, when we are talking about risk, we are not dealing with just any variable, but we are dealing with a very specific kind of a variable. We are doing a specific kind of a variable which is called the stochastic variable. Now, to understand why are we talking about stochasticity and probability, let us understand this concept of risk in a more detailed manner. So, let us understand what exactly is risk and how is this concept of stochasticity related to this concept of risk. So, what is risk first of all? Risk is a lottery. So, we define risk as a lottery. So basically, when a bank is actually giving out a credit to a borrower, right? So no matter how much risk modeling and how much of risk management and how much of whatever the bank might do, one thing is very important to understand, that moment the bank is actually giving out the loan, the bank is actually playing a lottery, because with that, the moment the bank gives out the loan, there are two possibilities which get created. No matter how much you manage for risk and how much analytics you do, there are two possibilities. One possibility is that the borrower turns out good and gives back the money. The second is that the borrower becomes Vijay Mallya and he escapes from the country without paying back the loan. So that is good and bad. So over here, there are chances associated with good and bad. So the fact that the borrower who has taken the loan may turn out to be good would have a certain chance, and the borrower who has taken the loan would turn out to be bad would also have a certain chance, right? So obviously there would be a probability P of success and there would be a probability Q of failure, and it is this chance which is modeled or which is represented using probability. So chance or risk. Chance causes this risk, right? And this chance is represented using probability. Chance is represented using probability. Using probability. So therefore chance is represented using probability. Right? So that is the part where we need to bring in this concept of probability, and that is where we need to understand studying. We need to start understanding what exactly is this probability all about. So when I talk about probability, so probability or stochasticity and risk, chance, everything. So probability is the mathematical way of modeling risk. So what is this probability and how do I basically talk about it? So basically, uh, probability arises when the following two conditions are satisfied. First, whenever we are taking an action, right? So we know all the possible outcomes which can happen as a result of that action. So all possible outcomes are known. All possible outcomes are known. So all the possible outcomes are known. That's one. The second thing that happens over here is that which outcome will occur as a result of a particular action is not known. So which particular outcome will occur for a given action, that is not known. So which particular outcome will occur. So which particular outcome will occur is not known to us, is unknown. Now if these two characteristics are satisfied, right, only then can we say that yes, this distribution or this problem that we are talking about is a probabilistic problem. So basically there are outcomes, and which outcome will occur, which particular outcome will occur is not known to us. Right? So over here what we know is, so if I am looking into a stochastic framework, there are two possible outcomes. One is all possible outcomes are known, and second, which part of the outcome will occur is still unknown. So if this happens, now you see that if these two conditions are put together, this creates, or these two conditions together will create an atmosphere of uncertainty. So these two together creates an atmosphere of uncertainty. Clear? And it is this uncertainty which can be modeled using probability. And to understand probability, the simplest question that we can think about, the simplest question that we can actually think about is, the simplest question that we think about is that of a coin tossing example. So if I toss a coin, I know that all the possible outcomes are, so there are two possible outcomes. One is called a head, the other is called a tail, right? So I have these two possible outcomes. I have these two sets. One is a head and the other is a tail. And this set S that I have over here, this is called a sample space. So a sample space is nothing but the set of all the possible outcomes. Right? So over here, I know all the possible outcomes. I know that it's a head and it's a tail. Now, what if I toss a coin and the coin goes up? Right? Now, when the coin is up in the air, I don't know whether the coin will come down as a head or it will come down as a tail. So that means both the outcomes are random in nature. So it can be a head or it can be a tail. Also, given the fact that the first has been a head, and if I toss the second coin, there is no chance that, given that the first has come out heads, the second will also come out a head or a tail. So if a head comes up, that is absolutely independent of what has happened previously, right? So these events or these outcomes are absolutely random in nature. So so all I can do is I can actually calculate the chance of the occurrence. So the probability of head will be the number of cases favorable to the occurrence of head divided by the total number of occurrences. So it is 1 divided by 2. Therefore, the probability of heads to come up is half. Similarly, the probability of tails to come up is also half, because the probability of tails is the number of cases favorable to the occurrence of tail, which is 1, divided by the total number of occurrences, which is 2. Therefore, this probability of head and the probability of tail both have an equal probability of occurrence in this case. So what it says is, or what probability clearly states is, or very simply states is, that, man, there are these possible outcomes, and out of these possible outcomes there is only one possible there is one outcome which will actually occur, and that is where this probability, or that is, and to ascertain the chances of the occurrence, we use probability. Clear? Great, great. So the next part that we will talk about, or that we'll talk about, is the classical. So over here, when we discuss probability, or as we discuss the theory of probability, there are three important parts that we'll talk about. There are a few important theories that we'll talk about. First is the most basic form of probability theory, which we call the classical theory of probability. The classical theory of probability. Right? Now, after classical theory comes the mathematical theory of probability, which talks about probability in terms of random variables and all. Mathematical theory. And the third theory of probability that we talk about is the Bayesian theory. Nowadays, the Bayesian theory is coming up very strong, and people are actually exploring Bayesian theory, and there are a lot of these Bayesian techniques that people are actually using. So there is Bayesian theory. Right. So this is what we talk about in the next class. So we'll stop here for the day, right? So we have covered the major descriptive measures of central tendency, dispersion, skewness, as well as we have introduced ourselves to probability. Next week we will explore these three theories of probability in detail along with probability distributions. Right, so probability theory and distribution, completing the theory and distribution will take 3 classes. So we'll talk about probability, these three theories, and we'll start distribution next Sunday, and then we'll continue and close it next Saturday. After that, we move into sampling theory and distributions. Right? Great. Okay. So that's much from my end. Have a great week, guys, and we meet next Saturday. Thank you.